to see if we can get some understanding about the potential presence of such a term, and even its mathematical form, it's worthwhile thinking about what the presence of such a term would mean. Let's take a closer look at this equation, right? It's suggesting to us that I can take a closed path integral around a full loop of the electric field, and we know what that equals, right? That would equal minus the voltage going from one point A back to itself. And rather than getting 0 now, this is saying we might actually be getting something that has some prefactor in front, but something related somehow to some time derivative of magnetic flux through that given loop. So let's see if we can set up a physical situation like this. This is interesting. This means we could have a loop of wire, right, without any battery in it, right, and we could get a net voltage around a closed loop quite different from what we've been doing in our circuit analysis so far, but that can only occur if there's some kind of change in magnetic flux through our loop. So let's consider a given experiment then to try to, a thought experiment, to try to tease out what this might mean here. So let's consider then some kind of magnetic field situation. So I'm going to have some, magnet somewhere. I'm going to try to sketch out like the flat pole face of my magnet. And within the pole face of this magnet then, there's going to be a magnetic field that's pointing upward here through our page, something like this. Try to draw it. This is the magnetic field is pointing straight up. Looks something like so. And now what I want to do is I want to imagine having a wire go through here, right? Some wire loop. And then I'm going to have that loop moving. So let me try to draw a little sketch of what that might look like. I'm going to be connecting other things to my loop, so I don't want to kind of draw everything in quite yet. But I'm going to have some kind of a wire loop here doing something like this, right? And the whole idea is to give this loop, and I'm going to complete the loop in this region here also momentarily. The whole idea is that then this whole loop is going to be moving then off to the right. And as that loop moves off to the right, clearly I'm going to be including more and more magnetic field area through my loop. I'm going to be changing that magnetic flux, and the hope is that this is going to give me some understanding of how changing magnetic fluxes might actually be able to generate voltages around a closed loop, around a circuit. Help us to be able to maybe even drive current around a circuit. So to kind of flesh out that idea, on this side of my loop, outside of my magnetic field, far away from any interesting exotic effects, I'm just going to put here some kind of a resistor. And the claim then is that this wire loop moving through this magnetic field somehow or another can generate a whole voltage all the way around itself from point A to point A, and potentially even drive a current fully around that loop. Now, to get an understanding of how that might occur, let's draw the remaining wire in my loop, but I'm going to draw it as somewhat a thick wire because I want to think about the processes that are going on inside of this wire as it's moving. So here I'm going to draw it as a thick chunk of wire here, something like so. And I'm going to give parameters here to describe my loop. The width of the loop here I'm going to call L, and the velocity that this whole thing is moving along, right? The whole thing is traveling off in this direction with a given velocity, which I will call V. And now as my conductor is moving through this loop, the first thing we need to realize is that I have a magnetic field. So there are going to be forces that are experienced by any of the charges that make up my wires, in particular any of the free charges. And if I have any, for instance, positive free charges, we can use the Lorentz force law to determine the force that they feel. As they are carried along here with velocity v, if I do v, which is off to the right, and use my right-hand rule, cross b, right? They are all going to experience a downward force. And then what will happen before I even connect up my circuit, so let's just, disconnect the circuit here just for a second. If that circuit's disconnected, what's going to happen then is I'm going to be building up positive charges on this face of my conductor. Similarly, on the back face, if they happen to be negative charge carriers, I know that the negative charge carriers, the magnetic force they would feel would be in the opposite direction from that of the plus charges. They would feel magnetic forces upward, and they would end up gathering, say, on the top half of my moving chunk of a conductor. And potentially a better way to kind of picture this is to imagine that the circuit actually isn't connected here and here yet, right? So if I do this, clearly I'm going to build up these positive and negative charges. And when I do that, of course, they are going to generate internal to that conductor some electric field that's going to be pointing in this direction. So that what will happen is, so there's going to be an electric field pointing upward like that. So what's going to happen then is as this object is moving here off to the right, the magnetic forces are trying to pull positives to the bottom, leaving negatives on the top surface. And that process, though, will continue only to a certain point. It will continue to the point where the resulting electric field, which is trying to prevent that process because the positive charges really don't like each other, it's going to continue until the forces from that electric field balance the forces from the magnetic field. So, magnetic field. And before we, connect our wire yet, I will point out, of course, that if I have this whole loop moving off to the right like so, there's definitely going to be this kind of charge separation occurring even in the wires here coming in from the left and the right, but it's going to be in sort of the same direction. I'm going to end up with minus charges on the top halves of my wires and positive charges on the bottom halves, right? There will be electric fields along that wire, but those electric fields, notice, are all going to be perpendicular to the wires, so they aren't really going to generate any forces that are going to affect the flow of charge through my loop. So, I've still not connected up my circuit yet, but I think you can see immediately that once I do connect my circuit, this thing really works in many ways like a battery, because these positive charges up here hate each other. The magnetic field is preventing them from going backwards in this direction to cancel against the negative charges. So they really have no choice but to flow out along this wire. And what I end up with then is a current I that ends up flowing through my resistor back along the top portion of the loop, and it then completes the circuit where this thing then operates somewhat like the EMF in a battery, and I'm going to end up with current flowing around my loop, some net electromotive force driving things around the loop, even though there's no battery, and it all somehow seems to be associated with the presence of this magnetic field and the fact that I'm getting more and more magnetic field in here through my loop, some kind of change in the magnetic flux. So that's the qualitative picture. Let's try to get a little more quantitative. So if I think about the system, I'm looking at some equilibrium situation that's occurring here within my wires. And in that situation, what we know is that this charge separation occurs until the net force on these charges, this is when I'm dealing with now a perfect conductor or a nearly ideal conductor. Inside a perfect conductor, right, as we've said, when it reaches equilibrium, the net force on any charge has to be zero inside of that conductor. So that is going to have to equal 0. And that force is equal to the charge Q times the electric field. And that's normally in the past where we've stopped the discussion. In that case, you can just cancel out the charge Q, and you'll see that the electric field in a perfect conductor is always exactly 0. In this case, though, we are moving through a magnetic field with a velocity v. So additional terms are required. So there's going to be plus v cross b, the remainder of the Lorentz force law. And now what we see is that the condition for the perfect conductor is not that the electric field is zero, but that the electric field plus V cross B has to equal zero, or another way of phrasing it, of course, is that the electric field inside a perfect conductor traveling at velocity v is not zero, but it's minus V cross B for a perfect conductor. You'll get a similar but slightly different story if you have a resistive medium there. But let's just focus on a very good or a nearly perfect conductor. So I know now what the electric field inside here is going to be. So now I can continue along and try to calculate the voltage of this effective battery. So I'm going to consider 2 points around here on my battery. A is the minus side, and B is the positive side. And so the effective EMF of this battery system is going to be, of course, just the usual formula. It's going to be the voltage due to that electric field from A to B. And we know how to calculate that. That's minus the integral from A to B of the electric field dot dl. And again, notice this is exactly the way a normal battery functions, except in a battery, the outside energy source that creates this charge separation is some chemical reaction that's occurring until I get enough positive charges on the top and bottom to stop the chemical reaction. In this case, it's just a magnetic force that's driving that separation of charge. Now, to finish our computation here, we simply now are going to be integrating from A towards B minus E dot dl. We know how to do that, right? It's going to be minus A to B. We break out the dot product, so it's going to be the magnitude of the electric field inside there times the magnitude of the displacement dl times the cosine of the angle between them. But in this case, the electric field is pointing upward, while the path from A to B points downward. So the angle between the little displacements dl and the electric field is 180 degrees, the cosine of which gives us a minus 1, which will cancel nicely with the outside minus sign. Now, I happen to know the magnitude of the electric field in this case. The electric field in this case is V minus V cross B. The velocity is off to the right. The magnetic field is perpendicular out of the page. So this is going to be the magnitude of minus V cross B. And that magnitude is, of course, the cross product. Magnitude of V times the magnitude of B times the sine of the angle between them. As we just said, B is out of the page. V is off to the right. That is a perfect right angle at 90 degrees. And the sine of 90 is 1. And the magnitude of the velocity is just what we were calling V. The magnitude of the magnetic field vector is just what we've been calling B. So that's the magnitude of my electric field. So we've got quite a bit going on here. Let's try to tidy all of this up. There was an outside minus sign. There's this factor of V times B, which are constant. So I can pull those here out of the integral. So there's going to be a factor of VB. What's left inside the integral is integral from A to B, the magnitude of the little displacements dl. And then there was the factor of minus 1 from the cosine. Those minus signs, of course, cancel. The integral of dl, those are just the path lengths added up from the top to bottom of this conductor, which is what we had called L. So this is L. So the effective EMF of this battery is just, of this effective battery system is just V times B times L. Good. And that's acting like a battery of that particular EMF. Well, very good then. Now that we know the electromotive force that we're generating, I think it's a pretty quick calculation then to determine the current. we would simply pick some original starting point here, X, and we would then add up the voltages going around our circuit, right? As we go along this direction, we're going along the flow of the current through the resistor, so that will give us a minus IR. And then when we come this way, we're going from the minus to the positive terminal of our battery system, so to speak, of our EMF. So that will be plus the value that we had just calculated. So we determine then that 0 will be minus IR plus this EMF. So that then tells me that that is equal to minus IR plus VBL. And we can solve then. IR would go on to the other side of the equation with a plus sign. And to solve for I, we then have to divide by the factor of R that came along with it. And we're left just then with VBL over R. So we will definitely be drawing generating a flow of charge. We can drive a current through this resistor by simply having this system moving over with velocity v, and that seems to tie very nicely to the fact that as it's moving, we are increasing the magnetic flux through our circuit, and it looks like we're getting something along these lines, that we're getting a net voltage going around our loop that somehow is related to the flux, that this change in flux creates a situation that looks like we have some EMF or electromotive force driving charges around our circuit.